Problem 209, minimum size subarray sum. So we are given an array of positive integers. The array is called nums. We're also given a positive integer called target. We have to find the minimum length of a subarray whose sum is greater than or equal to that given target. Now, subarray is a contiguous non-empty sequence of elements of that array. If we cannot find such a subarray, then we have to return 0. So here is an array, and let's say target is 7. In this case, so this subarray does not qualify, does not meet the condition that its elements add up to at least 7. But let's say this one does satisfy that condition. So elements here does add up to at least 7. It's exactly 7, in fact. Also, this array would satisfy that condition. So will this array. But the shortest array, whose elements add up to at least 7, would be this one here, right? And this has length 1, so 1 is the answer in this case, okay? Now, it's obvious that, if we're not careful, we're going to end up doing something very inefficient. So a naive solution would examine every potential subarray defined by left and right boundary. And that's order of n squared, right? N is the number of elements in the array. So if we examine every potential sequence, contiguous sequence, then that's already O(n) squared. And if we also have to calculate the sum of all of these sequences from scratch, so that's even worse. That's O(n) cubed solution. So these are pretty inefficient, and it's obvious that if you look at the constraints in the problem, so n can go all the way to 10 to the 5, which is too much for a solution like this, okay? So we somehow have to not examine every potential subarray. We have to skip a whole bunch of them, but ideally we should not skip that shortest subarray which satisfies the condition that sum is greater than or equal to t. Okay? All right, so let's have a look at the following situation. Let's say we are currently examining some subarray from left to right, okay? Now, what should be the next subarray be? What next subarray should we examine? And I'm going to suggest that we just look at two separate situations. So case 1 and case 2, right? In case 1, let's consider the situation when this condition is not met. So the condition that sum is greater than t, greater than or equal to t, is not met. So it's not met. And in the second case, we'll consider a situation when that condition is met, in fact. Okay? So case 1, when this condition is not met, that means sum is not big enough. We need to increase sum. And we will increase sum by making this range larger. Okay? So we're going to add one more element to the right. So we're going to move right boundary, one element to the further right. And we're going to keep doing this, right? We're going to keep doing this while this condition is false. So if this condition is false, we're going to keep moving the right boundary further to the right, adding more and more elements, right? And each time we incorporate a new element, notice that we don't have to recalculate sum by going through the entire range over and over again. We can simply take this new element and add it to the sum. Okay? Very easy. Just single operation. Now, when we actually reach the point when sum is actually over, equal, or greater than t, then we are in case 2, right? And in this case, there is no point in further continuing to add more elements to the right, because we're going to only get a longer range which still satisfies this condition, but we only need the shortest one. So if we already have one that satisfies that condition, why look at the longer and longer ranges? So we should probably start removing the elements. But removing the elements from right, doesn't make sense, because if we've just added these elements to make this range have large enough sum, now removing these elements back, it's not good, because we've already been there. So why don't we remove elements from the left instead, right? So we would increment left. And here again, we don't need to recalculate the sum by going through the entire range, because we could simply subtract this number, the number that we've just removed, from the existing sum, and in a single operation, we're going to have a new value of sum. Okay? Now, we're going to start this algorithm by setting left and right both pointing to here, to the first element with index 0. So R and left and right both going to be equal to 0 initially. Then we're going to keep doing basically this. So increment right or increment left, depending on the first case or the second case. And we're going to keep going until R, the second boundary, goes through all of these elements of the array, so that each element gets a chance to be the last element in the shortest boundary that we're looking for, right? So R will get through all of these elements, and we're not going to stop until R goes beyond the first element, beyond the last element. And once we are looking at this very last element, when R is looking at the very last element, L will also keep being incremented until we get to the range which does not meet this condition anymore. Okay, so if it's strictly less than target, there is no point in continuing this algorithm anymore, because even if we cannot expand this to the right, obviously, no more elements, and there is no point in removing anything from here, because we're only going to get worse sum, lower. We're only going to lower the sum, which is already low, right? So with this, I'm going to convince you that we're definitely going to find with this algorithm the correct answer. And I'm going to convince you by saying that at some point with this idea, we're going to look at the shortest range that satisfies this condition. Even though we're going to skip a whole bunch of other ranges, the one range, or maybe even multiple shorter ranges, if there are more than one shortest ranges with this condition, then we're going to go through all of them. So we're not going to skip those ranges that do matter. Okay? How am I going to prove that? Well, this is probably almost obvious, but I'm still going to give you a formal proof, but it's not going to be pretty. It's often the case in maths that something that is pretty obvious that still needs a proof mathematically. So I would not be, for example, satisfied. I would never start writing this until I'm happy, until I've satisfied my curiosity beyond any doubt that this will actually work, right? So I would need a formal proof. But it's not going to be pretty. It's going to be probably more confusing than what I've said so far. But I'll still give you that proof. And you're welcome to skip over that proof. So here is the proof. Maybe you can find an easier proof. So the first kind of lemma that I'm going to prove is that with these conditions, L will always be less than or equal to R plus 1, okay? And if you look at this, when this is actually an equality, when L equals R plus 1, we are actually looking at an empty range, okay? Because if L and R are exactly the same, then you're looking at a range with one element. And if this is the beginning, left, yeah, but it actually ends before it begins, then this is an empty range, okay? So this is effectively an empty range when you have a strict equality here, when you have an equality here, that's an empty range. So the worst that we can get is an empty range. We're never going to get anything worse than that. So when, say, beginning is two spaces, two indices before the beginning, yeah, the worst could be that the end is one space before the beginning. That's already kind of confusing, probably, right? So how do I prove this? Now, look at these two conditions. Well, first of all, initially this condition is met, right? I'm going to go through an induction. So if you see here, initially left and right are both 0, and this condition is true. So, but later, can we break this condition ever? Well, we can't, because this move, oops, what happened? So this move will never break this inequality, because it will only make it stronger, obviously, if we increment R. What could break our condition is when we increment left boundary. But notice when we're going to increment the left boundary, when that condition is actually met. And if that condition is met, then we are not looking at an empty array. Sum must be greater than or equal to a positive target. So sum is a positive number, which means we're not going to be looking at an empty array. So L is less than or equal to R. That's the only case when we get the chance to increment L. And if you increment L in a case like this, you're still going to have this condition met. Okay? Good. So I think we've convinced ourselves that this will always be true. Now, think about the following. So I'm going to prove to you a few things. So first of all, left and right, when they're going to enter this range. So they can already be in the range if the range starts from the first element. But either way, when R is about to enter, the furthest L can be is that first element, right? Because it cannot be anywhere here, because that gap would be too big and it would not satisfy this. So when R is about to enter, L could be here, and that's when R will enter, right? So when R comes in, and R will at some point definitely come in, because I said I'm not going to stop this algorithm until R goes through every element, right? So when R comes in, left could be anywhere here. It cannot be any further than that. So left is somewhere here when R does come in eventually into our range. That's already obvious. Now, the next thing I'm going to show you is R cannot leave this range until L actually enters the range. Okay? So L could already be here, or it could be somewhere to the left, but R cannot leave the range until L does enter. Okay? I'll prove that quickly. Why cannot R leave? So let's say R is about to leave. R has to come to the last element, and L hasn't entered. It's somewhere to the left of the range. Now, how can R leave? It can only leave if that is met, which means if that condition is not met, right? So sum must be strictly less than t, which is impossible because the sum includes our range. Sum includes our range and some other numbers as well. So it definitely cannot be strictly less than t. So we would never increment r, we would increment L. So that proves that R cannot leave that range until L does come in. Okay, so R comes in, L could be at the first element or somewhere before. R will not leave this range until L does actually come in. And if L does come in, it cannot budge. This is the next thing I'm going to prove. If L does come in, it cannot budge beyond the first element until R gets to the last element. And you probably see how together, all of these statements together give you the thing that we're going to be looking at the entire range at some point. L looking at the first element and R looking at the last element. So the only thing left to prove here is that once L does come in, R cannot leave. L will not go past the first element until right boundary gets to the last element. That's also easy to prove. Let's say R hasn't reached the last element. Okay, then this cannot increment. Why? Because L gets incremented only in this case when this condition is met. So sum must be greater than or equal to t. So this sum must be greater or equal to t. But that's impossible because in that case, this would be the shortest range. This would be the shortest range which satisfies this condition, which is shorter than whatever we initially presupposed. So that's not possible. That cannot be the shortest range. That cannot have a sum greater than or equal to t. So that means L cannot get incremented until R reaches the last element, which means eventually we'll be looking at the situation where L is still at the first element and R reaches the last element at some point. Okay? Now, that means we're going to examine every potential range that needs to be examined. We're going to obviously skip a whole bunch of ranges because instead of examining O order of n squared, we're going to actually examine O order of n, right? O of n. So we're going to skip a whole bunch of ranges here. Why are we going to be why is going to be O of n? Because if you look at this, left and right only move in the positive direction, right? So at most, at the worst case, both of them, we're going to kind of traverse this entire array. So it's going to be like 2n operations, right? So 2n different ranges that we can potentially examine here, which is obviously On. Great. And then since we're not recalculating sum is being recalculated by a single operation, the entire complexity of this whole thing would be On. Yeah. So we're going to skip a whole bunch of ranges here, but as we just proved, we're not going to skip those ranges that do matter. The shortest ranges that have that quality where sum is greater than or equal to target. Great. So just to mention one more thing, I'm going to have a min length variable, min length. I'm going to set it to plus infinity initially. And then every time I am looking at the condition where sum is greater than or equal to target, I'm going to reevaluate min length and potentially overwrite it with a shorter length. Okay? Now, I'm going to write, so it's time to implement this now, right? Let me just copy this function to typescriptlang.org, right? I'm going to write it here, typescriptlang.org. So we said let sum equals 0, let left equals 0. What else? Let min length equals plus infinity. And now excuse me, excuse me. Now what I'm going to do is this is going to be slightly strange after this introduction, this explanation of the algorithm, but I'm going to have two nested loops. The for loop outside. So let right equal 0. Right should be less than num's length and plus right. Okay. So every time we come into this loop, we need to recalculate sum, right? Because right has just been increased. Or maybe we just came here for the first time, which is right has just been set to 0. So sum needs to be recalculated, and it needs to incorporate this element. So num's right. Excuse me. Okay, so sum is now correct. Now it's time to, so we've incremented, we've moved right. So now it's time to get left a chance to move to the right until this condition is no longer true. Okay? So I'm going to say while sum is greater than or equal to target, we have to do what? So first of all, sum needs to be recalculated, and we have to remove num's right, num's left. We need to remove the first number, and then we also have to post decrement left. So this will have the effect that sum would be correctly recalculated. So this would be removed. Sum left would be removed. And after that, left would be decremented. I mean, not exactly. So this num left will be taken. Then this will be left would be reduced. And then num left would then be subtracted from sum. Strictly speaking, that would be the exact order of operations. Now, we also need to recalculate mean length. Mean length is what? The minimum value of itself. Yeah, because why? Because while we are inside this loop, this sum is greater than the target while we are inside this loop. So we have to look at the length of this array. So what will be the length of this array? This subarray, sorry. The length would be, well, I think it's better to put this in the opposite order. So while the sum is here, we haven't budged, so we haven't moved left or anything. So we are looking actually at the subarray that actually satisfies this. Because if we do this after this, so if we do it like this, then right and left are actually no longer necessarily satisfy this condition. Okay? So before I mess up left, while I'm looking at this range, which actually does have this condition, I have to recalculate mean length. And the new length would be right minus left plus 1, correct? That's the length of the current range, which does satisfy this condition. So I update mean length, and then I can look at the new range. Okay? Now, this kind of doesn't look precisely what we discussed here, right? You might be slightly surprised, because the way I discussed this algorithm is as if those two cases were exactly symmetrical, not some sort of nested two nested ifs, one for loop and one while loop. So I was talking about this situation that when this condition is met, then we increment left, otherwise we increment right. So it kind of, but I think you can satisfy yourself easily that this is actually a very neat way of writing that. And it's a very short and elegant way of writing that. This will have exactly the same effect. If you look at this, the first time we set right to 0 and left to 0. Okay. So then left gets a chance to increment as many times, 0 or as many times as required to bring sum down under the target. Okay? While this is done, then we need to increment right. And that's precisely what's going to happen by the outer loop. Now, what if right needs to be incremented multiple times? Well, in that case, this loop will not be entered. So the outer loop will just increment right as many times as required without ever entering this loop. See, that's an elegant part here, because if you were to write this algorithm the way I just described it, it would be slightly more convoluted. Yeah. So this is just an elegant way, I think, to write this algorithm. But still remember that how symmetrical the idea is, even though the implementation isn't really that symmetrical. Now, you can also notice that the sum and left can potentially go inside this definition of the loop, right? You could say sum equals 0 here and left equals 0. All of this, maybe actually, you know what, maybe like this. You could do that. Min length cannot go inside because we need min length outside of the loop. But probably this is not as pretty, so I'll just keep those two variables outside. But min length we need here because we're going to return min length with a small kind of twist that if min length remained infinity, remained unchanged, that indicates for sure that we haven't even updated it once, so we didn't even reach one range that satisfies this condition. Therefore, no range exists, because we proved that if one range existed, then we would always find it. Since we have never found it, so this has never run, this command, that means we've never entered this while loop, this never happened. So min length is infinity. This is the case when they tell us if there is no such subarray, return 0. So we're going to return if min length equals plus infinity, then we're going to return 0. Otherwise, we're going to return min length itself. Yeah? So that should be it. That's our program. Okay, copy it here. Let's fold it. And we can now run these pre-tests. Wrong answer. Why do we have a wrong answer? So what did I do? Let me just quickly examine. Min length is infinity, left is 0, sum is 0. Right 0. While sum is greater than that, right minus left plus 1. And then sum is, oh, sorry. This should be plus plus. Yeah, this is obviously plus plus. I mean, we never move left to the right, left to the left. We move left to the right. So we're going to increment left. Yeah. Okay, so we have to make that correction here. Run this again. So the pretests were useful. Okay, now we have everything is right. And now I can submit. Let me fold this again. And let's submit this to the actual suite of tests. Okay, so we beat 93% of all the solutions in terms of time. Memory is just 14%, which is always surprising to me. How is that possible? Again, we just have like 3 or 4 variables. Yeah, we just have 4 integers in addition to what was given. So we only beat 14% or 15% of other solutions, which is quite incredible. Okay, but that's the solution.